So from geotagged photos to driving directions, being able to handle geospatial information is an increasingly important part of a lot of web apps. Anthony Joseph is a software engineer, mathematician, and startup co-founder. He's going to introduce us to GeoDjango, the module built into Django's core that lets you add these sort of capabilities to your app. Please make Anthony feel welcome.
Cool. So good to go? Cool. Thank you very much for the warm welcome. So my name is Anthony. I'm going to be giving a talk to you about GeoDjango. I've called this the traveler's guide in the sense of like if you're traveling to a new country, I'm just going to show you the main sites. For the more advanced travelers, I might show some of the cooler things to go and try out later on, but I'm hoping that it's going to be fun for everyone. Before I get started, I guess for the international guests as well, we do like to acknowledge the traditional custodians. Being in a mapping-based talk, I figured I might actually show a map, circa 1700s. And we are actually somewhere here, which is roughly the Gadigal people on the Eora Nation. So I'd like to acknowledge the elders past, present, and future. Also in my talk, I'll be mentioning a few vendors just out of conflicts of interest. I've been a customer of some of these vendors, but I'm not sponsored in any way. But I will take tips if anyone has any. So yeah, it's going to be one of those talks. Just to give you an overview, I'm going to just introduce some of the fundamental mapping concepts, and then kind of work our way from the bottom up of our stack, how we store data, how we query it, and then display it, and some of the future directions, and if I get the time, maybe some Q&A. And unless you want me to be in your photos, I will post the slide deck on the Slack DjangoCon channel, so you all can go and take a look at it in your own time. So some of the fundamentals of mapping. We'll go back to the very beginning, a latitude and longitude coordinate. This happens to be the Sydney Opera House. For me, it kind of was the question of, well, what does it actually mean to have a coordinate, latitude, longitude? So we're going to dive pretty much straight in. We have a geographic coordinate system is when we talk latitude and longitude. So what that actually means is we have a 3D spherical approximation of the Earth, and the latitude and longitudes are actually angles from the central points. By far and large, the most commonly used coordinate system is WGS84, World Geodetic System. This number, 4362, comes up a bit later, so just as a bit of a callback for later on, just keep that in mind. So if we were to describe where we are roughly there, we would actually have the central point here, and the latitude and longitude would actually be the angle to roughly there and down. But there's a much better diagram in the next slide. Like that. So what are the advantages and disadvantages of using a geographic coordinate system? Well, firstly, there's no distortions. That'll come in a later point, the next slide. And also, we can represent virtually any point in the world. If we do want to do analysis on a geographic coordinate system, it does become a bit more complicated, because what actually happens is if we had a point here and another point here, we have to use the method of great circles to calculate distance and area, and that is computationally expensive. So it can affect things like query performance. But there's a more fundamental point of, well, we've got this 3D approximation of the Earth. How do we display something in 3D in 2 dimensions, like a map, like a physical printed map or a computer screen, And the obligatory conference, XKCD comic. There's one for every season, isn't there? So in order to actually represent a 3D object in a 2D surface, we would use a projected coordinate system. The Mercator projection is probably one of the most common ones we've probably seen around. And there's a web-based version called Web Mercator. For the Australian audience here, there is the Geocentric Datum of Australia, 1994, sorry. It's tapping my slide, which is probably the more commonly used ones for representing Australian data. Some of the advantages of this is that it's great for displaying on, well, a web map, and it's also great for analysis. But that comes a little asterisk, because The analysis will work well if it's within the area that you're actually projecting on. So if you try, let's say, use the geocentric datum of Australia for another part of the world, you probably have distortions. And that can affect the quality of the accuracy of your analysis. So I was actually hoping that, figured no subtext here with using Canberra in my slide deck here. We do have two common types of geospatial data, vectors and rasters. I saw this one of a very ambitious analyst in Canberra who went and cycled around Parliament House to kind of create the shape of the Millennium Falcon. I thought that would be a kind of a cool thing to show. It was between that or the Uber surge pricing model, so I figured, what would the rebellion do? That's vectors, typical straight lines, that kind of content. Rasters are also referenced in the documentation. As you can imagine, it's a bitmap, x and y coordinate with a value that corresponds to it. In this case here, this is an elevation model of Australia, so the value at the xy coordinate would be the relative elevation to sea level. I've seen it mentioned a lot in the documentation, but I'm still to see like people using rasters in anger in a production web map sense, but just for completeness, I want to include that here. So some of the data structures we use in vectors, we have our standard point, latitude, longitude, all kinds of goodness with that. We also have lines, so we'll have simple start and finish point for a single line. This happens to be the so-called latte line. I'll go into that a little bit later on. Or we can have my very lousy CD to surf time, 1 hour and something minutes. It's a very high number. So that's a polyline, which will be a series of lines connected together to create something like a path. We can also have polygons, as you can imagine, any number side shape. And this happens to be part of the City of Sydney federal electorate. The reason I say partly of, because that's one polygon, and we can also have multi-polygons. As it turns out, the federal seat of Sydney has both Sydney and Lord Howe Island. Random bit of trivia for everyone here. Much like if you were to store a floating point number in an integer, you'd pretty much get truncation. If you try to store a multi-polygon in a polygon, you'll only get one of those. So that's something to really keep in mind. I made that mistake before. So building on those simple data structures, I'll just talk a bit about the analytical concepts that one can use. So geocoding is one that is commonly used. So we'll take a street address, so like 130 George Street, Sydney, and it gives us a latitude and longitude. Reverse geocoding, as you can imagine, is the opposite, where we give it a latitude and longitude, and we say, well, what address would this happen to correspond? And it can be a one-to-many relationship. So 130 George Street happens to be the Museum of Contemporary Art. So you can get multiple results if you are doing a reverse geocode. Geolocation's another commonly used point where we give a latitude and longitude. Sorry, we give an IP address, and we get a latitude and longitude. So this could be used, say, for fraud. If a customer is connecting to your server, like on a web app, and they have an IP address that's in the US, and they're an Australian-based customer, that could send up a flag in your fraud system. But we can also use geolocation in autocomplete. So if we are typing in a street address and we know our users are in Sydney, we can suggest them Sydney addresses instead of anywhere else in the world if they happen to type in a street address. We also have routing, where we would have a start and end point. So this is the Opera House and walking to the Museum of Contemporary Art. It's a nice walk if you want to get out and stretch your legs during the conference. Routing would typically use like a road network, public transport data to show how to get from one place to another. So walking would naturally prefer things like pedestrian safe footpaths to actual roads, probably would avoid people walking on freeways. Public transport would usually combine walking with a public transport timetable, like you walk out to the local bus stop, catch a bus to part of your destination and walk the other part. Cycling is an interesting one because it can also use road networks as well as any bike paths. And depending on your routing algorithm, it can prefer bike paths over like roads. and the obligatory driving, taxi, and ride sharing. So building up from that, we can do spatial analysis. So on the left is a climate forecast model where they're representing forecasts across, well, this is actually for the world, on a map. And you can kind of get a lot more contextual information from that, from showing on a map. And this is the latte line that I was mentioning before. So what particularly talented analyst has done, they've actually looked at relative socioeconomic advantages, and they've been able to come up with this line showing lower advantaged areas over more advantage. It happens to almost divide the city. And the last concept I'll go through is isochrones. Iso being same, chrone being time-ish. I don't speak Latin. This is how far essentially you can travel within a certain time. So this isochrone happens to be somewhere in the middle of Sydney. How far can we go in 30 minutes traveling by public transport? And you end up with some very interesting, at least for me personally, answers where, as it turns out, if you're traveling starting the city, we can actually get up to somewhere near Vaucluse, which is like probably where a bus stop is. So you can kind of do some pretty interesting analysis through isochrones. So storing geospatial data. So this is what everyone probably came for, probably not. How would we store it? There's web services like web map services, web coverage, servers like GeoServers will be able to host this content for you, or more likely, formats like well-known text, KML, good old KML from way back when, GeoJSON, and a couple of proprietary formats, ArcGIS shapefiles, mapinfo tab files. They've tried to standardize these with the Open Geospatial Consortium, and they also have tried to standardize database formats for storing spatial information. So if we take our good old-fashioned Postgres database and add GIS, geospatial information systems capabilities onto it, we get PostGIS, SQLite plus GIS equals SpatialLite, and there are spatial extensions for MySQL, Microsoft SQL, Oracle, even some of the NoSQL style databases like MongoDB have spatial extensions. So I'm not expecting anyone to read this. This is more of a compatibility list of all the functions that are available to our users and what database engine. So Postgres, as you could imagine, does actually do quite a lot. Oh, that's not working at all that well. Does actually do some of the advanced functions, but if your existing database engine for your current products are using the other ones, you're not limited by that. So just something to keep in mind if you were to start from scratch. And if you remember before when we were talking about the different data types, they happen to map very nicely to the different fields in our database. So a point would store in a point field, multi-point field. Lines would be stored in a line string or multi-lines, and polygons being in a polygon field or multi-polygon field. So this is where, now I'm trying to call back to period bits of my talk. If you are storing geospatial data, by default, it will store it in that WGS84 standard, that SRID 4362, which that's why I was kind of mentioning the number, because by default, or if you wanted to change it, you would have to use that number. It also will create a spatial index by default. And another thing that I learned during my travels was if you set geography equals true, what can happen is if you are doing distance calculations, the database engine will make certain assumptions that it won't normally do, and it can help with query performance. And why do I kind of bring up spatial reference systems, these SRIDs? More often than not, if you are using like a KML style format or you're getting data from like some other service, they will be in that format. If you are getting data from official sources like the Public Sector Mapping Agency, one of the government-owned companies, they will give you data in this GDA 94 standard. So you will need to do a process called reprojection, where you convert data in one projection into another. More importantly, I guess, kind of calling back to previous talks, make sure you read the documentation, read the metadata associated with the data that you are getting, because they will answer a lot of the questions, answer a lot of the assumptions that are made. I also want to talk really quickly about spatial indexes. Your normal database indexes would be typically B trees, if you set that index equals true on that field. If you do use that spatial index equals true, you end up with what I think is something pretty cool, where you will have, let's say your polygons. What it'll actually do is it'll create a bounding box around all the different polygons, and it'll store that in its index. And this can help our query performance again. So another thing to kind of keep in mind if you are looking to structure your database in a certain way. So querying geospatial data. Everyone loves query sets, right? Just as much as we would do with our regular query set, we just substitute instead of our, count, or not count, like something like, amount is less than or equal to some query value. We just, instead of a count, we will substitute in a geospatial function, something like, distance is less than or equal to. So it will be like, location, distance is less than or equal to some point. But I'll go through a couple of examples just to kind of show some of the more common query types you might encounter. So point in a polygon. That's kind of a standard query that one might have if you have a polygon shape. What we'll have, I've created this example of just like a suburb, and we want to kind of find points that happen to lie within that. So if we had a postcode and a boundary, the boundary being stored as a polygon field, what we would do is we would have this suburb, and we'll filter along, and the boundary happens to contain that point. So that is one way that we can find this point here, and this one wouldn't happen to be in that point. So another one is, within a particular, from a central point, what is within a 2 kilometer or some fixed distance. As you can imagine, this might be interesting for like a simple web app showing like the stores. It happens to be for like a company's website. So if you had like the location, you could say, is the location within whatever the user's point is and the fixed distance. So you can see we're just using the traditional ORM, but with the geospatial functions to do queries and query our data sets. Another thing I like is also sorting by distance. So you can imagine what's the closest store to wherever the customer is located. So for this, we kind of need to do something a little bit more special, like we need to annotate our queries. So in this case here, we'll annotate with the distance of location from whatever the location is in our data, in our particular one, to the point, and then we'll order by that distance. I've kind of been really heavily talking about distances, but there are a whole bunch of other functions out there for you. So things like length, perimeter. So yeah, you can even change the output, which I thought was pretty cool. I've never really tried that yet. So that's something I actually want to try out in spare time. So now we've got our data. We've found a way to store it. We've found a way to query it. Let's try showing it to our users. So we've managed to find a way of actually storing our spatial data. If we actually want to display it, we would not only need our actual data, but we also need a web mapping library and a base map. So web mapping libraries typically tend to be JavaScript-based. 3 examples happen to be OpenLayers, Leaflet, or Mapbox. Mapbox actually hired the lead developer for Leaflet to work on the core product, so they've kind of incorporated bits of that into their mapping library, and of course, Google Maps. If you're developing for mobile apps, there's usually a lot of the mapping vendors will have their own SDKs. And we also have the base map. So this will be the tile imagery that kind of sits behind whatever data you're showing. So you can have graphics like your typical Google Maps, Mapbox, OpenStreetMap, ArcGIS, and so on. You can also use satellite imagery. Digital Globe seems to be like the world leader in a lot of this, and a lot of the maps that you see will be using Digital Globe imagery. Nearmap is an Australian company that does some pretty cool imagery. Like it's very, very high resolution, very high detail, so they do some pretty cool stuff. And the US government, like Landsat and like, they have their own low resolution maybe ones, but at no cost. And they'll come in a particular URL format that would work with your web map library. This slide, I just want to show just some of the examples of base maps just around the convention center area. So this is like the typical Apple Maps, Google Maps using its satellite imagery, Google Maps with the regular like map view. Here Maps as loosely affiliated with Nokia at some point, kind of thought where that happened, and Mapbox Maps. Some of these mapping engines will let you customize the colors, customize what information gets shown. So it's kind of a decision for you in terms of what you want to use. Like, do you want to show more data? Do you want to make it accessible for users? Do you want to fit your corporate branding? There's a lot of choice out there to make. And I'm not going to kind of recommend one, it's just to show there's actually a lot of different ways to show the same information. So I'm going to kind of try a little bit brave here and do like a example here. So in this one here, we have our usual preamble, just loading, style sheets and JavaScript. But more importantly, when we go through, we have a div that has the map, and we can obviously size it in whatever way to kind of fit our page. For this one here, we would define the map. This is using Leaflet, by the way. And we would set the original view, like where it's going to be located. And the number here at the end is the zoom level. This is how far the map is zoomed in when the page loads. We then load a tile layer. So this, I'm happy to use OpenStreetMap. That's that URL that I was mentioning before that we get from whatever map we're using. And typically I had to put like an attribution. The attribution text was really, really long, so I kind of just cut it short just for this example. And then we go and add it to the map. And finally, we actually add the marker that we wanted to add. So we've got our latitude, longitude, add to map. We bind a pop-up saying, hey, you are here, and then open it up. And we end up with something like this. Not too complicated, but I imagine some of the cluier people were probably thinking like, you're using latitude and longitude, and isn't that the geographic coordinate system that you mentioned before? But that's 3 dimensions, and you're showing it on a map. That's 2 dimensions, so what's happening here? As it turns out, web maps will automatically reproject your latitude and longitudes to the Web Mercator projections, so they will automatically figure it out for you. So they'll make our lives a lot easier. And just to kind of bring that all back to a close, there's also Forms API as well, which I actually got to copy the previous slide, which I'd had the model API on, into the Forms one, because they have the same structure, and the docs have a little bit more in that for you. So just want to just kind of wrap up a little bit with some of the future directions. So if you had used the GeoDjango before, some of the cool things that are kind of happening in this space. Naturally, you might not want to dive straight into doing like web maps. If you want to do some more offline analysis, QGIS is an open source program that you could use to do your analysis before you go and write your scripts and the like. ArcGIS is a commercially available tool that does very, very similar work. If you are interested in the more data analytics side, Tableau and to a lesser extent Power BI can do that. Everyone in the big data space is GeoMesa, which is adding the geospatial extensions to, I guess, the big data toolkit. There's also WebGL maps, so people are trying to port the existing tile-based imagery into WebGL. So that is something that you can consider as well if it kind of suits your use case. There's also mobile things happening in the mobile space. So 3D graphics, so people, I think Mapbox in particular, are using Unity for to show like spatial data, and also using augmented reality, virtual reality for things like routing. So you can have your phone up, and it'll show you which way to walk through a city. Another couple of things would be open data. So where actually can you get data from? Data.gov.au actually has a wealth of spatial information out there. So it kind of goes across various jurisdictions, some at the federal level, some at the different states. So that's a good source if you want to play around with just some data just to see how things work. There is also government data. So this is still data you might have to pay for, but is still curated by the government. So at least for the Australian audience, Public Sector Mapping Agency, they collate things like the road network for all of Australia. They standardize a lot of those features across the country, things like election boundaries. A lot of that stuff happens at the PSMA. They're also doing some really cool things now with satellite imagery. So they have a new API, their Buildings API, where you put in a latitude, longitude, and it says, at this latitude, longitude, here happens to be a building. It has a swimming pool. There's this much green area around it. So they're doing some pretty cool stuff there. And if you want to use commercial data, there is for the geolocation that happens to be MaxMind and IP2 location. But my one advice would be check your licenses. Some of the open data is like Creative Commons license. We might have to attribute or might not be for commercial use, so just keep that in mind. Another thing that's happening in the spatial world, particularly for Australia, this actually kind of gets into the details of geospatial analysis, is the tectonic plates are always moving, so much so that we actually need to create a new datum for Australia. So before we were using GDA 94, tectonic plates have moved so much that Geoscience Australia, which is the agency that's responsible for a lot of, like the USGS, but for Australia, they're actually developing a new datum, GDA 2020. So this will affect a lot of the data that's produced by government departments. But much like before, just read the metadata, and there are tools that will help automatically reproject stuff for you. So just something to keep in mind in the next few years. So I thought I'd just kind of wrap up quickly with a couple of the things that I learned from over the past couple of years. For me, it's more of a personal statement. Like, geospatial analysis is a bit like statistics. It's easy to do something that looks right, but have some fundamental issues at it. And so just tread carefully if you do start to do this kind of analysis. The official docs, I think GeoDjango has a lot of commercial interest in it. I think Eventbrite actively contribute to it, and a few other commercial companies. So the docs are actually pretty well maintained, and I use the docs quite a bit in actually drafting my slides. So don't be afraid to use them. When you are dealing with geospatial data, be really careful of coordinate systems, of license, of coverage. So I did mention the PSMA. They're great, but they only are interested in Australia. So if you are the archetypal startup starting out in Australia and then want to go global, you might need to think about who is providing your data and what coverage they might have, because some might have better coverage than others. But above all, check the metadata. I'm ashamed to say that I actually have made mistakes where I haven't read the metadata and tried to do analysis, and I've got like, what am I looking at? And it's been the metadata. To kind of steal stuff from the security people, don't roll your own crypto. Try to avoid, if you can, writing your own libraries when you're doing geospatial analysis, because a lot of talented people have already written them for you, and they will kind of help a lot with a lot of the analysis and a lot of the assumptions that you may make. So thank you very much. I don't know if we have time for questions. Probably not time for questions. Hit me up on the Slack channel. I'll put my slides there, but just trying to grab me around the conference. But thank you very much, everyone.